Alright, and welcome back everyone. In this video we're going to go over another example. We're going to go over our next example for separable ordinary differential equation. So what I have here is an example of what's known as a separable ODE. Okay? Alright, separable ordinary differential equation. And okay, some of you who are smarter than I am probably already know that this right here, this equation is actually a very commonly encountered equation in heat transfer or thermodynamics. This is called Newton's law of cooling. Newton's law of cooling. All right, let's see. So the method that we're going to use to solve this differential equation, as you guys have already guessed by now, is going to be separating the variables, because it's a separable ODE. Here on the right side, I have my initial condition, and I also have the value of my lumped parameter, h times a divided by rho CPV. All right, I know that. And also I know the value of my T infinity. My T infinity is going to be the ambient temperature. All right, with that said, let's proceed and let's see if we can solve this problem analytically, of course. All right, so I'm going to rewrite this as the derivative times the 0.05, that's the value of my lumped parameters, minus 298. Okay, so now let's see what happens if I divide both sides by 298. Let's see if I can divide both sides by this expression. If I divide both sides by this expression, hopefully I'll be able to get all the temperature terms on one side and everything else on the right side. And as you guys can see, this cancels out, and what I'm left with is the temperature divided by, well, 1 over the temperature minus 298, not to forget the change with respect to time, and the negative 0.05. all right, now at this point we can separate the variables, because on the left side our expression is just a function of, let me use different color schemes, this is not good, is a function of the dependent variable, which is our temperature. And now at this point we can just separate the variables, so that's what I'm going to do next. All right, dt, the time term on the other side, and now let's see if we can integrate this. All right, so I hope some of you have brushed up on your integral calc and can see that this comes out to be natural log of temperature minus 298. And on the right side, I hope you guys can see that this comes out to be 0.05 multiplied by time plus the constant of integration, which I'm going to write as a. Now, in order to find the value of a, in order to get our solution, or to get our unique solution, we need the value of this constant of integration. For that, we're going to use our initial condition. And as you guys remember, our initial condition as written above was that the value of temperature at T equals 0 is equal to 500 Kelvin. Okay, so once we use that, we're gonna get natural log of 500 minus 298, and that equals a, because as you guys can see, this time term is gonna go out, because that's gonna be set equal to 0, because that's the temperature at T equals 0. All right, a comes out to be, now I can just rewrite this as a equals natural log of 500 minus 298. Oops, what is that? I believe that's 202. All right, let's roll with this. We have our constant of integration set up, and our final solution, let's zoom out a little. Our final solution is going to look something like this. So the solution to our differential equation is going to be natural log. Let's use a different color tone. Okay. Natural log of temperature minus 298 divided by 202 is equal to negative 0.05 times t. Okay, so if you guys are wondering how I used when I plug this back in and get to this final result, I'm just using some properties of logarithm. Okay, all right, so I can rewrite this if I want to make it explicit. If I want to make it explicit in the, if I want to make my equation explicit in the temperature, then by doing some algebra, the steps that I'm going to skip is going to look something like this. So all right, there was a negative here. I believe there was a negative here. I'm missing a negative sign. Sorry about that. Let's see what's above here for a second. All right, there's a negative sign there. So this comes out to be 298 plus 202 e to the power minus 0.05 times t. So that's going to be my solution in its explicit form. All right, so just to give you guys a quick recap, sorry about that. We have our differential equation, and the name used in heat transfer textbooks is Newton's law of cooling, and I had my initial condition and I had the values for my parameters, and the method that I've used here is separation of variables. This method right here, the things that I've done here is called separation of variables. Okay, if you grab a DiffEq textbook, if you grab a differential equations textbook, this is the terminology that they're going to be using. After plugging in my initial condition, I was able to solve for the constant of integration, and here I have my general solution. All right, my general solution in the form of in explicit in temperature. Okay, all right, thank you so much for watching, guys. I hope this was helpful.